Okay, so what we saw is called a fold bifurcation, in the sense that the picture is something like this. Okay, so there is one stable and one unstable solution, and these are the parameter and the state. Now, this kind of a curve can occur anywhere. You could have a situation like this. This is the state, this is the parameter. Okay, but you could have below this particular value there is no solution. Above that particular value there are two solutions. One is stable and one is unstable. So this is what we call a canonical form, where the critical point is placed at the origin. But in general, you could have a solution structure like this, which would be typically a quadratic, a parabola. Quadratic type of nonlinearity will give rise to that. Now, the next type of nonlinearity is a cubic type of nonlinearity. Okay, so here you have this is called a pitchfork bifurcation, and you will see why it is once you map out the state space. So dx dt equals ax minus bx cubed. Once again, x is the state variable. A and b are parameters. There are two parameters in this problem. Okay, so it's like Reynolds number and Prandtl number. Now, both the parameters are positive, we are told. Okay, and first task is to get the steady state solution. So I'm reinforcing that idea. The same steps are involved. Steady state f of x equal to 0. Solve that, and what do you get? You get xs equal to 0 is one solution, because you can take xs as a common factor from this. And then what you will get is, like for example, you can write this as xs times a minus b xs square equal to 0, factoring xs out. That means xs equal to 0 is one solution, and from the second part you get xs equal to plus or minus square root of a over b. So there are three solutions possible, because it's a cubic equation, right? There are three solutions possible. So remember, why did we put a and b greater than 0? Can you tell? So that you have a real solution. A and b, either one cannot be negative. So both are positive. We restrict ourselves to that case. Okay. So when you plot that, what you will find is that there is one solution like that, one solution like that, and then one solution on the axis itself, because xs equal to 0 is a solution. That's why it's called a pitchfork solution, bifurcation. It looks like a fork. Okay, and we need to determine the stability of this branch, stability of that branch, and these two branches. So below the value, a certain critical value, there is only one solution. Above a certain critical value, there are three solutions. And how does the stability change? To answer the stability question, we need to linearize the dynamical equation, which we do as before. Dx prime dt equals f of xs plus df dx at xs multiplied by x prime. Higher order terms we are going to drop out. Okay, so f of xs is equal to 0, because that's how we define the steady state. So df dx is a minus 3b x square. Then plug x equal to x. Okay, so when x is equal to 0, what happens to this Jacobian j? When x is equal to 0, this is j. Remember, this whole thing is the Jacobian, the derivative of the function evaluated at the steady state. Okay, so when x is equal to 0, that simply becomes a. And when a is less than 0, what happens to the stability? Is stable. So this part is stable. When a is greater than 0, it is yeah, right. When a is less than 0, it's negative, so it's stable. When a is greater than 0, it's unstable. True. But we are going to cheat. We are going to let a alone be negative. A could be positive or negative. I think I should have read this actually, probably. A comma b greater than 0. The meaning of that is a could be anything, but b is greater than 0. So it's my mistake. Thank you for catching that. Okay, so a could be anything, but b is greater than 0. Now, when a is less than 0, this particular steady state is stable, and when a is greater than 0, it is unstable. So that is this horizontal line. Remember, on the horizontal line, x, we are plotting x on the y-axis. So xs is 0. Okay, and then take the second solution that we have, which is x is equal to plus or minus square root of a over b, and plug that in. Okay, so you're going to get a minus 3b times square of that, which is going to be a over b. Right? Square of xs. Xs is a over b. So when you square that, this will give you b, that is equal to, I mean, this cancels b, is equal to minus 2a. So for a greater than 0, what happens? A greater than 0, this becomes stable because it is negative. Okay, so this is a stable solution, and that is a stable solution. Okay, so for a greater than 0, we have 3 solutions, 2 of which are stable, 1 is unstable. For a less than 0, we have only 1 real solution, and that is stable. And this is called a pitchfork bifurcation. Again, the idea is how to find the steady states, how to probe their stability by linearizing it, finding the eigenvalues, finding the sign of the real parts of the eigenvalues. That's the key idea. Any questions on that? Okay. So that's the bifurcation diagram. Okay, so here it says that these are stable. They will be attracted towards that steady state. Whereas this is unstable. So even if you're close enough to it, it will actually go away from there. Okay, so that's an unstable solution. These, the upper one and the lower one, are stable, and this one is stable. The typical convention is any solid line you indicate by as a stable solution, dashed line you indicate by an unstable solution. The third example, now we are going from a first order system to a second order system, or 2 first order equations. So here we have 2 ordinary differential equations. The state variable consists of x and y. There are 2 states, so there are 2 equations. There is a parameter a, okay, and x and y that appear on the right hand side are states. Okay, so we need to go through the same process. Now by inspection, first we need to find out what is the steady state. Okay, now we need to solve these 2 equations simultaneously to find x and y value at which those 2 functions are 0. Okay, so you have f1 equal to 0, which is this equation, and that is which is f2 equal to 0. But f1 is a function of both x and y, and f2 is a function of both x and y. You want both of them to be equal to 0. And one solution that satisfies that is xs, ys equal to 0. By inspection, you can verify that. If you put x equal to 0, y equal to 0 in those 2 functions, you will find that the whole thing is 0. Okay, so that is a steady state. And the question is, we have to ask the question, is that steady state stable or not? And if it is unstable, what happens? Okay, and this is a very important type of dynamical behavior. Lorentz equation and a number of other equations coming from fluid mechanics, chemical reaction engineering, they all exhibit this kind of a behavior. It's called a Hopf bifurcation. Now, for a 2 by 2 system, what do you need? You need to construct the linearization process. The idea is exactly the same. Okay, but you will linearize both the functions f1 and f2, and you will get a 2 by 2 matrix because each function is a function of 2 variables, x and y. So you have df1 dx, df1 dy, df2 dx, df2 dy. Take all the 4 partial derivatives, arrange it by a 2 by 2 matrix. That is your Jacobian, the linearized Jacobian. And you need to evaluate that at x equal to 0, at y equal to 0. That is at the steady state. And it turns out when you do that, you will get the Jacobian like this: a minus 1, 1 minus a. Okay, the linearized equations are given here. You should verify these things. Okay. So when I have a 2 by 2 system, I need to calculate the eigenvalue. For 1 by 1 system, j is the eigenvalue. For 2 by 2 system, the eigenvalue problem is j minus lambda I equal to 0. J is a 2 by 2 matrix. I is a 2 by 2 matrix. And set the determinant of that equal to 0. Solve for lambda. That's your eigenvalue. And in this case, the eigenvalues become a plus or minus I. I is the complex square root of minus 1. Okay. So the solution for this one is going to be in the form of x prime y prime equals some constant, say alpha 1, alpha 2 times e to the power a plus or minus I t. Okay, that's how the solution will look like for the perturbation variable x prime and y prime. So once again, how do you determine the stability? What do you want A to be? A is the real part of the eigenvalue. The eigenvalue is A plus or minus square root of I. The real part of eigenvalue is A. So you want A to be negative for the solution to be stable. Okay, and if A is greater than 0, it becomes unstable. But what happens at A equal to 0? In the previous case, the eigenvalue itself was 0. But in this case, is the eigenvalue 0? No, the eigenvalue is plus minus square root of I. So if I have that, here is a question. It's something that we did in complex variables. E to the power plus minus it. That is your x prime and y prime. So what will the trajectory look like? Sines and cosines. It's an oscillation. Okay, it gives rise to a sustained oscillation. Okay, so that point is called a Hopf bifurcation point. It's a point at which your steady state loses stability and it gives rise to a periodic solution, a solution that has a certain period. Okay, so this is your state space x and y now, and if I start with some initial condition, the trajectory in the state space may look like this with time, and then it reaches a steady state. So the same thing, if you plot x versus t or y versus t, you would call that as a time series, the same trajectory. Starting from some initial point, it may reach a steady state like this. So this curve is parameterized with respect to t. So this will be at some time t1, sometime t2, etc. So starting at t0, going up to t infinity at this point. That is a steady state. Once you reach a steady state, x and y doesn't change. The point simply becomes a constant in the state space. Okay? But as you keep increasing A, this trajectory will change its shape. And for a certain value of that parameter A equal to 0, in this particular case, if you start from this trajectory, just goes down, and watch what happens carefully. And that's it. It'll just keep on going on that circle. Okay? It's a closed orbit. It's not a circle, it's a closed orbit. And if you start at a point in the interior, it'll also go and join the same curve. And that is called a limit cycle. That's one of the important dynamical features. Okay? At a certain critical value of the parameter in a problem, a number of problems exhibit this phenomena, what happens is the trajectory forms a closed cycle. Okay? And as you continue to increase the parameter, two such closed cycles may merge and give rise to what is called a strange attractor. Okay? The terminology that is used is, for example, a steady state is an attractor, meaning no matter where you start from the state space, the trajectory is attracted to that particular steady state. That's an attractor. A limit cycle is a particular form of an attractor because it attracts all the trajectories in the neighborhood to a closed curve. A strange attractor is one which attracts it to a certain region, but it never forms a closed curve. So in going from 1D to 2D, we saw this limit cycle appearing as an object. We go from two-dimensional equations to 3D equations. Three equations, Lorentz equation is an example of that. You can form the so-called strange attractors. Okay? Any questions? The math is not very difficult in these, but the concepts are very important. You need to understand that because turbulence is about formation of these transitions from laminar flow to through these transitions, eventually leading up to turbulent flow. So we're going to see this various examples of instability in flow. Now, in this particular case, you can transform the x and y into polar coordinates r and theta by using the transformation x equals r cos theta, y equals r sin theta. Subjected to the differential equation can be transformed from xy to r theta. It becomes simple. And then the trajectory itself can be solved because this can be integrated. So the trajectory is basically theta going round and round with time in linearly, and the radius either increasing or decreasing or forming a circle. Okay, so here you can see when a becomes negative, that term is going to go to 0. So you will basically get the radius of the trajectory to be equal to a. And this is indicated graphically in the following picture. So this is the bifurcation diagram for a Hopf bifurcation. For a less than 0, you have a stable solution. For a greater than 0, the steady state becomes unstable. But at any value of a, if you take a plane, cut a plane like that, on that plane you will have a circular trajectory. Okay, remember this is y, that is x. So in this graph, this is the y-axis, that is the x-axis. That's the state space. In that state space, if you start from anywhere, it will go on to this circle. That's the limit cycle. The size of the limit cycle keeps on increasing with increasing value of a. And this point is called the Hopf bifurcation point, where the steady state becomes unstable but gives rise to a stable limit cycle, stable closed orbit. And the key feature that we noticed is that the eigenvalues have a pair of purely imaginary eigenvalues. Okay, that is, lambda becomes simply plus or minus I. This is the map of the real part of the eigenvalue, and that's the imaginary part of the eigenvalue. As the parameter a changes, when the parameter a is negative, you have two eigenvalues here. As you keep parameter going to 0, these eigenvalues, these are path of the eigenvalues as the parameter changes. At a equal to 0, the eigenvalues cross that imaginary axis, meaning they have only purely imaginary values. As a becomes positive, the eigenvalues continue to go to the right hand side. If any of the eigenvalues move to the right hand side, what happens? You have not been following whatever I've been saying. The eigenvalue, this map shows the eigenvalues for any dynamical system. If you have 10 eigenvalues, you plot all the 10 eigenvalues. They must all be on the left side of this axis. Why? Because we are plotting the real part of the eigenvalue against the imaginary part of the eigenvalue. Okay? So if any of the eigenvalue appears on the right hand side, what happens to the system? It becomes unstable because you have a real part that is positive. So for stability, all the eigenvalues must be on the left hand side. Control system design is exactly about that, moving the eigenvalues, placing the poles on the left hand side so that you have a stable feedback control system, for example. Okay, the same mathematically it's the same concept. So in fluid mechanics we have the same requirement that if you have a lot of eigenvalues, make sure that they are all on the left hand side for the flow to be stable. Now, in the case of fluid mechanics, as you change the parameter, you may drift to the right hand side, the flow becomes unstable, and that's what gives rise to chaotic oscillatory solutions, which are part of the turbulent characteristics of the turbulence flow. Turbulent flow is inherently time dependent, okay, because there are always velocities that change with time, with high frequency fluctuations. Any questions? Okay, Lorentz attractor. I heard that you have already seen this in another course. Okay, this is a very classic paper done in 1963 by Lorentz at MIT, and the paper is entitled Deterministic Non-Periodic Flow, and it actually appeared in Journal of Atmospheric Sciences. What is the problem about? The problem is about solving the convective flow in atmosphere. Okay, weather prediction. He was working on modeling weather prediction. We all know weather prediction is a pretty challenging task, even though it is governed by Navier-Stokes equation. Still, it's a very challenging problem. We are not able to predict beyond 5 days with any reliability. Why is that? And that was answered basically by his study. And what he was doing was, in fact, I think I have. This was his study, the Lorentz attractor. Basically, he took the Navier-Stokes equation. One thing that you should be able to do, I don't know whether you can see this because it's not a very good image. Can you see it at the back? let me go through a quick quiz. Okay, what are these various terms? From this course, if you come across a paper like this, you should at least be able to say this term represents this or stands for that. Okay, I think this is a typo. That should have been a psi. Psi is the stream function. We have seen the definition for stream function. U equals d psi dz, w equals d psi dx. He's looking at how many dimensions is he considering in this problem? 2. X and z. It's a 2D problem. So naturally introduce the stream function. Okay. What does this term stand for? It's from the Navier-Stokes equation. It is a time-dependent term. What does this term stand for? Yeah? Convective acceleration. Okay, the v dot del v term. Okay, so this entire thing stands for the convective acceleration. What does this term stand for? Viscous term. We have seen that e square psi, for example. He just calls it del square psi. Okay, so the viscosity is there. What does this term stand for? Very good. Okay, that term stands for thermal buoyancy, temperature gradient that causes density to change, that causes the flow to emerge. So he was studying the thermal instability in atmosphere, rolling off when you have a hot fluid at the bottom, cold fluid at the top. Cold fluid wants to descend, so there is a rollover of the atmosphere. So he's basically developing a model for that. The second equation is the energy balance equation. Again, here it's a transient term, and this is the convective term. How do you know it's a convective term? You have d psi dx. D psi dx is u. Okay, and then this is the conductive term. And what is this term? We haven't seen that, so it's a trick question. What d psi dx is u, you know that. Okay, so u times delta t. What could that be? The forced convection term is here, right? That's the velocity that carries the energy with it. This is the forced convection. This is the heat conduction. This is the natural convection term. So this is a mixed convection problem. So if you know this carefully, you will see that temperature affects the velocity and velocity affects the temperature. It's a coupled problem. Okay. So that is really, I guess we haven't really talked about it. So let's not. I won't probe you more onto that. What he did was he took these equations. These are obviously very complicated partial differential equations, nonlinear. And in 60s, we didn't have enough computing power to be able to solve that. So he devised a mathematical technique for developing what is called a reduced order model. Okay, so he did a Fourier analysis, took the temperature gradient in the vertical direction, temperature gradient in the horizontal direction, and reduced these equations to 3 equations. And those 3 equations are the equations that you will see as Lorentz equation, commonly cited. I guess I don't have it here, but I have it in the notes. So let me. Okay. So dx dt equals pr times y minus x. X stands for velocity, y stands for one temperature difference, z stands for another temperature difference. So there are 3 equations that he derived. And it had a number of parameters. Prandtl number is 1, and there are 3 states, x, y, and z. Okay, and r is another parameter in the problem, and b is another parameter in the problem. So there are 3 parameters, and he reduced the entire Navier-Stokes energy equation to these 3 equations, focusing on the very primary important variables. Okay, so x, y, z are the states, are the unknowns. P, r, and b are the parameters. You should be able to, if I give you this problem in the final exam, you should be able to do these analysis. What is the steady state? Okay, as a function of the parameter in the problem, and determine the stability of those steady states by linearizing that equation, finding the eigenvalues. Okay, but what he did was he took these equations and chose a particular value of the parameter set. PR equals 10, B equals 3/8, R equals 28. Okay, and he integrated them numerically on his computer. In the 60s, you can imagine what kind of a computer. You probably wouldn't have even seen it because you're all very young. These are teletype things that will just do and print out the numbers. Okay, so he let the computer run. For solving 3 equations, he had to let it run overnight. So he let it run with some starting initial condition. The next morning he comes and look at the results. They are all printed out in his paper, and he says, okay, I want to continue this some more. So he takes the last 3 states, x, y, z, that he output, says that's going to be my initial condition, and start integrating again. But when he took that and fed in the value, it was calculating up to 6 digits. He just took 3 significant digits and put it in there, and then he was getting a completely different trajectory. Okay, and this was a very keen observation. You don't discard something like that. He said, why is my solution so dependent on the initial condition? Why do I have to put all 6 significant digits? And since then, it has come to be known as sensitive dependence on the initial condition as one of the features of any chaotic system. And what he saw was this kind of a picture. It looks totally random. We have a fully deterministic model. We have 3 well-known equations, well-defined equations. You should expect some sort of a nice behavior, but this is the kind of behavior that he saw. Sometimes it's in the up part, sometimes it's in the down part, and you cannot really predict. If you make a slight difference in your initial condition, in the 4th decimal place, you will get a picture that looks completely different. Okay, and these are some of the characteristic features of any chaotic system, and weather prediction is a chaotic system. The essence of it is captured in this particular model. And another feature is it's another way of representing that, which has become very popular, is called the butterfly effect. Have you heard of butterfly effect? What is? Right, a butterfly in Australia, the disturbance that it sets can create a tsunami or a tornado somewhere else, right? So the sensitive dependence on initial condition, the long-term unpredictability, and the global nature of the effect. Okay, these are all encapsulated for the first time, and so this has become a very popular topic to consider. There's a whole book devoted to Lorentz attractors. It looks at all the theoretical framework that was published in the 80s. Over a 20-year period, there was a lot of activities. Now, if you go to Wolfram Alpha, this is a website built by Mathematica, you will find a lot of these interactive learning tools, and for Lorentz attractor there is one. Okay, it's basically what you see here is the trajectory in a 3-dimensional projection, so you can actually flip this over any way and see. And there are 3 parameters, B, R, and sigma. Okay, you can slide these parameters to anything that you want and see how the solution changes. Okay, and this is the time interval over which you want to integrate. Okay, and these are the initial conditions. You can play with each one of them. Let me just probe to give you some idea of what do we mean by a steady state, what do we mean by a periodic state, what do we mean by a chaotic state. I'm not sure whether I can pick the right values for each one of them, but let's just try it. Okay, so the initial condition here is 1. Let me just pick all of them to be 1. 1, 1, and 1. Okay, so the initial state is somewhere here. 1, 1, and 1 in the 3-dimensional space that is projected onto this 2D. Now, as I start integrating the differential equation, the trajectory goes like this. In a cyclical fashion, goes towards that point. So there is a steady state there. Okay, once it reaches a steady state, what happens to that curve? The curve will not move any further. It will just stay there. Okay, so what kind of an approach to the steady state is this? It is a decaying oscillation. If you plotted x versus time, or y versus time, or z versus time, you will get a decaying oscillation. So it's a stable steady state. Now, as I increase the parameters, I need to see what happens to this. So sigma equals 100, I have a steady state. Okay, so let me go to the other value. You see what happens here as I pass across 12.6 something? I guess I should maybe give you a different view. Okay, this is the view, and I'm going to change sigma to a smaller value. This is going to take a long time if I do it like this. Don't have a precise control. Pardon me? Yeah, make any observation you want to. I want to. Oh, can I type it? Why didn't I think of it? Okay, 2.2, 3, 4, 5. I guess. Okay, so 18, 20. So it really occurs somewhere between 5 and 10. You need to use a bisection. So this is 5. Let's try 15. The same. What happened? Can you kind of picture how the trajectory is located for this particular case? There was one set of circles on this side for low value of sigma. And then as it changes to 15, it goes there. But each one has a stable steady state. So the starting point is here for 15, but the trajectory switches to the other side and reaches a stable steady state. If I had this as 5, it will just go around here and reach a steady state. So you have a pitchfork bifurcation. There are two steady states that are stable. Depending on where you start, it will go to either one or the other. Okay? And as you continue to scan this parameter, let me do it 5 one more time. You can see that, right? So 5 is the larger, slowly varying circle, and 15 switches to the other side. Okay. Now, as I continue to change this, what you will find is that these two, there will be two limit cycles that form at a particular value of sigma, and these values have been calculated and documented in that paper. But I'm not sure that I'm going to be able to. Okay, I think it's probably this parameter then. There. That would be called a strange attractor. So the trajectory doesn't close on either one of them. There are two limit cycles that have kind of merged with each other, and the trajectory just goes between, flying between the two. Okay, and that is called a strange attractor. When you take this and plot it as a time series, x versus time, y versus time, that's when you get a picture like what he saw. Okay, so this is a time series, but if you take the same thing and plot it on a state space, you will get a picture like this. I would encourage you to go and play with this, because you can get, these are great new tools that are coming out where you can actually interactively sharpen your intuition to see whether what you have learned conceptually agrees with the actual model. You can program any differential equation into this and use this tool to kind of study the response. Okay, so a strange attractor is nothing but a closed space in a three-dimensional state space where the trajectory lives forever. No matter where you start, it will be attracted to that. But it's not a closed cycle, it's not a steady state, it's not a limit cycle. And these have the characteristic features of sensitive dependence on initial condition, so you can never be able to predict where it will be at a particular time. It will depend very sensitively on what your initial condition is. And turbulence, if you look at the turbulent velocity profile, it will have signatures exactly like this. If I measure the velocity at a particular point, it will look completely random. It will look completely describable only by statistical means. So statistics is a big tool that has been used in looking at turbulent flows. Any questions? So that is the state space projection of XYZ in the so-called strange attractor. So you start anywhere, it's going to be attracted to that particular region, and then it just keeps going back and forth like this, never crossing the trajectory. One of the results from ordinary differential equation theory is a trajectory cannot cross itself. Why cannot it cross itself? If I have a state space, for example, I have a two-dimensional system, x1 and x2, or x and y, and I have two differential equations, dx1 dt equals f1, dx2 dt equals f2. The trajectory of this in the state space is going to be something like this. I start from here and I end there, steady state. Okay? Or the other possibility is that it starts and closes on itself, which is a limit cycle. Okay? Steady state, a limit cycle. But a trajectory can never do this. Why can't it do that? There's a theory that states that it cannot do it. Okay, there's a theorem that proves that. The reason is very simple to understand geometrically. If this were my starting point, if that intersection point were my starting point, which direction should I go? There is ambiguity, right? Because if this were my starting point, how do I calculate the trajectory? I take the starting point, put it into the right hand side for F1 and F2. F1 and F2 I can calculate because you have given me x1 0 and x2 0, the initial condition. Take the initial condition, plug it in here, I know F1 and F2. What does F1 and F2 tell me? It tells me the tangent, dx1 dt, dx2 dt, the direction in which I should go. Okay, so using that tangent direction, I calculate where the next point is. Using that as the initial condition, I continue. This is what the Rangakada method, all the other methods do to construct the solution numerically. But if I'm at a point of intersection, then the tangent is not defined uniquely because there are multiple definitions. Since these functions f1 and f2 are continuous, you cannot have multiple values. And so that's not possible. And that means in a complicated diagram like this, the trajectory can never cross. So these are called space-filling curves. These curves, if you continue to integrate, eventually will fill the space because they can never intersect. They never form a closed, except for limit cycle. The limit cycle forms a closed cycle, and hence the tangent is uniquely defined at every point on the trajectory. Okay? I know I'm laying out a lot in this lecture. You need to go through and review these. Okay? So much for the basic idea of stability of a dynamical system and linearization and bifurcations. How does the nature of the stability changes? Now we need to transfer all these ideas into fluid mechanics. Okay? Lorentz did that, and we just saw it as his final result. Now we are going to go through the process very similar to what Lorentz did. How do I take the Navier-Stokes equation? How do I linearize the Navier-Stokes equation? How do I put perturbations of various frequencies? How do I assess the stability? And this one is called the method of normal modes. Okay. So the basic idea is, if you give me a flow field, I'm going to take that flow field and perturb it, the steady state flow field. Okay. So I know the steady state, and I'm going to impose various perturbations, vibrations, for example, of very small amplitude because I want to look at the linear stability. Remember, when we talked about the Poiseuille flow in a pipe, I said that the flow becomes unstable around Reynolds number of 2100. Where does the disturbance come? The disturbance comes from your pump, from any vibrations in the lab. Small disturbance can trigger that. In that particular case, I've also told you that there are experiments that have been conducted recently where they removed all the sources of perturbations, and they were able to maintain the laminar flow, parabolic flow, for Reynolds number as high as 100,000. Okay? So it is the small perturbations that cause the flow to become spontaneously unstable. So how can we impose these perturbations? And that is what is done by the normal mode analysis. So this is the basic state, the basic steady state flow. For example, the parabolic flow in a pipe that's given to you. That's one dimensional. Okay? And we are going to decompose it into basic flow and a perturbation flow. And the perturbation flow, exactly as we did in the previous case, is the perturbations can be now spatial. That's a thing that adds complexity to it. We have looked at only ordinary differential equations. Now we are looking at partial differential equations. So the perturbations would be spatially varying, and we are going to capture that by this kind of an expression: e to the power I kx, e to the power I m z, and e to the power sigma t. Those are the nature of the perturbations, with y as the unknown. So the problem that we are going to in fact look at is the flow between two parallel plates. Think of that. Okay, this is x, that is y, and we have a parabolic profile. Two parallel plates, infinitely long parallel plates. It's a two-dimensional flow. Okay, so in the perpendicular direction, everything is uniform. So we're going to consider that case. So u of y is given, the velocity profile, the basic profile. On that profile, we are going to put a disturbance, superpose a disturbance, which is going to be written as some unknown disturbance in the y direction, but the disturbance in the x direction and the z direction is going to be periodic. So I'm going to put a periodic disturbance, a very small magnitude periodic disturbance. Why should I consider only periodic disturbance? Because it's infinitely long, right? That's the only function that will kind of repeat itself infinitely long. So in the x direction and in the z direction, I have ikx and imz. That gives me the sines and the cosines. That is the basic idea of the Fourier analysis. Okay? And what do I want to compute from this? I want to compute sigma, my eigenvalue, and make sure that the real part of that eigenvalue is negative for stability. That would mean that the disturbance, the periodic disturbance I put, will decay with time. Then the flow will be considered as stable. Now k and m are called wave numbers. These are just integer numbers. And you will have then basically sine kx or sine my, etc. Okay? And we need the real part of sigma, which is sigma r, to be negative for stability. And sigma r equal to 0 represents neutral stability. So the idea is translated now to a partial differential equation. So the math is going to be nothing new. We have seen before, but we are going to outline the steps involved in there. Now, this kind of an analysis has been done for a number of problems. I think at the beginning of the course, we already saw that Taylor vortices, that is flow between two rotating cylinders. This is the inner cylinder, and that is the outer cylinder. And the one-dimensional flow we actually analytically solved in the class. Okay, and we put what Taylor did was put a perturbation exactly along the lines that we studied and solved the eigenvalue problem, determined when that flow becomes unstable. When it becomes unstable, what happens? So he was able to predict that the flow will form these cells, counter-rotating cells. He was able to predict the wavelength, the distance between two cells. Okay, so he was able to predict at what rotational speed, at what Taylor number, that the flow will become unstable from a one-dimensional flow to a two-dimensional flow. And these are some of the experimental examples. So this is going from 1D to 2D, one dimension to two dimension. This is going from 2D to 3D, time dependent. So this is called a wavy flow. So it forms, if you look at it with time, what will happen is these waves will move with respect to time. These are called traveling waves. It's as if the wave is traveling in the azimuthal direction, in the angular direction. And what he did was predict the 1D to 2D stability. This was done much, much later. That's one example where the stability analysis has been applied. Another example is the so-called Rayleigh-Bernard problem, which is the heat transfer counterpart. Okay? In this case, what are the mechanisms that we talked about? It's a centrifugal force against the viscous force. The centrifugal force is a destabilizing mechanism, meaning if I have a fluid particle that is in the interior, that is moving at a faster velocity, this will have a tendency to be thrown out by centrifugal force. Okay? And that's what causes this kind of a flow outwards. Of course, it must return, so it will come back like this. So it's called a centrifugal instability, where centrifugal force overcomes viscous force. Viscous force has a damping mechanism. Okay? And in the Rayleigh-Bernard convection problem, you have heated and cooled plates. So the bottom plate is at a higher temperature, the top plate is at a lower temperature. The temperature gradient is like this. And this temperature difference is your driving force. Once you exceed a critical temperature difference, you will find that the flow again becomes from no flow to flow. The no flow condition is what? There's no velocity. It's just by conduction. Heat is being transferred from the bottom plate to the top plate by conduction. And of course, gravity is acting this way. Okay? So this is called a gravitational instability or buoyancy driven instability. So if just like in the previous case where a faster moving inner fluid element gets thrown out by centrifugal force, here what happens? A fluid element that's at a lower level at a higher temperature becomes lighter and wants to rise up. Okay? That is the driving destabilizing mechanism that causes these convection currents like this, going up and coming down. That happens only when you exceed a certain critical heating rate, and you will find cells like these. These are called roll cells, but in this case there are also other complicated cell patterns that can form, called hexagonal cells. Okay, and that is a Rayleigh-Bénard problem in heat transfer, which is caused by buoyancy-driven instability. And fingering instability. This is a case where you have two fluids, or there is a density gradient in the fluid. Okay, so this is, for example, you have salt solution at the top and water at the bottom. Salt solution has a higher density. Okay, and there is a clear interface. You separate them initially and then partition it, for example, by putting a block of sheet of plastic material, and then remove that at time t equal to 0. The salt will start falling down. Okay, and these are called fingering instabilities. They are also studied using the same framework, okay, of normal mode analysis. This is a beautiful picture. You know what this is? This is called the Kelvin-Helmholtz instability. And the setup here is you have two liquids, the heavy liquid at the bottom, okay, and the light liquid at the top. This is on a tilting plate. Okay, so you keep it initially horizontal, and at some time t equal to 0 you tilt it. What would happen? The heavier fluid will start sliding down like this, and the lighter fluid will start going up, just to satisfy continuity. So it creates a shear between these two fluids, and the shear basically deforms the interface. This is again an instability mechanism. Okay, and there's a beautiful picture of this from nature. Somebody took a picture of this in atmosphere. Just look at it, you see such a beautiful pattern, and that's a Kelvin-Helmholtz instability. What is happening there? There are winds that are shearing. There is a shear layer right there. Okay, maybe wind is flowing that way here and that way there, and it is visualized for us luckily by a dark cloud. Otherwise, when winds are going like this, there may be these instabilities forming, but we won't be able to see. But in this particular case, there is a dark cloud that formed in that line, so it kind of highlights that Kelvin-Helmholtz instability. Now, Taylor analysis, what did he do? So we are going to now go through the mathematics. We've seen a physical example, physical mechanisms that cause these instabilities, centrifugal, buoyancy, sometimes Coriolis force, things like that. So in the Taylor case, what we do is we take the two-dimensional assumption, okay, reduce the Navier-Stokes equation for those two dimensions, okay, and that's what you will get, UR, U theta, and UZ. The velocity is in all three directions, but they depend only on two spatial variables. So the flow is two-dimensional, but all three velocity components are present, and this is your continuity equation. This you should be able to do. Okay, simplifying the Navier-Stokes equation under that assumption. Okay, and then this is a nonlinear equation. For example, you have U theta square here, and here you have UR, U theta, products of nonlinear terms. You need to linearize that. Okay. So the idea that we did for ordinary differential equations, we are now implementing it. U bar is equal to the steady state value, capital U, plus this U, which is the perturbation. So this is the perturbation. The base state, the steady state, is given by UR is 0, UZ is 0, V theta as a function of R, one-dimensional flow. For that, we know this, the equation is reduced to this, the solution reduces to that. This you should be able to do, getting this solution, for example, okay, in your general exam or final exam. So what we are interested in is this solution stable for any perturbation? Okay, and the way we do that, I've just shown you the final result, is for you to take this, use in the 2D Navier-Stokes equation. Let me label them as A. Okay, so this set of equations. That is a two-dimensional Navier-Stokes equation that we simplified, imposing two-dimensionality. And take this, plug it in there, okay? And treat U as known, treat P as known. These are the velocity and pressure profiles of the one-dimensional steady state for which we want to know the stability, okay? And the lowercase u and the lowercase p are the perturbations. So take that into the Navier-Stokes equation, and the steady state part will basically cancel out because it satisfies. So what you will get is an equation for the perturbation variable small u and small p. And these are the perturbed equations. That will require some challenging effort on your part to show how you get that into the linearized version of the perturbation part. Okay, but notice in here these appear because those are the known steady states. The known steady states will influence the solution for the perturbation. Now it's not easy to solve this equation because it's linear, because we have linearized it, but still it's a partial differential equation. So we introduce a normal mode. Okay, and the normal mode says that I'm going to introduce a perturbation that is periodic in Z. Okay, we're still considering only axisymmetric flows. So there is only variation is in the Z direction, which is periodic. And the time we want to check whether the sigma is, the real part of sigma is negative or positive. So we take those perturbation equations and impose this normal mode solution on that. That means take this, plug it into this equation. Use it there. Use a normal mode solution into there. And again, after one page of algebra, you will get these two equations. These are now ordinary differential equations in that single variable R. Okay, so that's an eigenvalue problem, and in here you will notice sigma appears. That's the unknown that we need to solve for sigma. We need to still integrate these ODEs. Okay, and here you have Taylor number appearing as a parameter. So put various values of Taylor number and get out the sigma and check whether that sigma, the real part of the sigma, is negative. Then you know for that Taylor number the flow is stable. You will not form cells, you will have just one-dimensional flow. But if there is any value of Taylor number for which this is positive, then the cellular flow will develop. And that was done by Taylor in 1923. And there are a number of other parameters here. The ratio of inner to outer cylinder rotational speed, the gap between the two cylinders. These are all parameters in there. But the Taylor number itself is defined like this. And he developed as a solution to that, and the solution I won't hold you responsible because it requires you to solve it on a computer. And the solution is presented in this graphical form. Okay, so the system is stable. This is the neutral stability curve. Okay, as a function of the rotational speed of the outer cylinder versus the rotational speed of the inner cylinder. Okay, so if you are above that, the system is going to be unstable. If you're below that, it's going to be stable. And earlier, Rayleigh did an analysis of the inviscid flow. What is inviscid flow? Do you remember?
Irrotational.
Irrotational. When you throw the viscous term completely. Okay. So he found the stability boundary to be this. That is solving the Euler equation. Similar problem for the Euler equation. But Taylor did for the full Navier-Stokes equation and obtained the data points are his experiments. He did experiments to see where the transition occurs. The solid line is the theory that he did. And that's one of the first success stories on hydrodynamic stability. And since then, Rayleigh-Bernard problem, Kelvin-Helmholtz problem, they've all been studied in the same framework. But he basically developed the framework, did experiments, and confirmed that the idea works. Any questions on that? So when a problem like this, I'm really presenting it to you very quickly. Let me just reiterate what I expect you to be able to grasp and manipulate. Okay, so if I give you a problem like the Taylor-Coe problem, you should be able to get the solutions. That's for granted because you've done a number of assignments. One-dimensional problem, get a solution to that. Okay, and Linearization I would expect you to do. Okay, that is getting this. So I would ask you to go through that step to get the linearized equations. Okay, and normal mode, I won't ask you to be responsible for getting this equation or the analysis, but you should be exposed to it. Like what are the basic ideas behind it, and how does one construct the stability diagram? This is a stability diagram where there are parameters, and you identify which range of the parameters you have stable system, which range you have unstable system. Any questions? And any of the ODE model equations that we studied for pitchfork, for fold, for hop, you should be able to manage that in an exam. Okay. I think maybe that's enough for stability. There is another one, an important equation called the Orr-Sommerfeld equation. And it's the same idea. There are no new ideas. It goes through the process of linearization and process of defining the stream function and the normal mode analysis to get at this eigenvalue problem called the Orr-Sommerfeld equation. So I'm not going to hold you responsible for the final exam, but I would encourage you to study it on your own. We're not going to be able to cover it in the next 6 minutes or so. But it is in the notes, so go through that. It will help you understand the idea of linearization because I have worked this out in greater detail, how to linearize the Navier-Stokes equation. I think I will stop there because I'm running out of energy. Any questions? The last lecture we will devote it mostly to turbulent flows. Okay, we'll look at what is turbulence, what are the turbulence models available, and if there is time I will talk a little bit about dispersion, and that's another topic conceptually you should be exposed to. And then the last 20 minutes or so we will review the whole thing that we did in this course, and if you have any questions on any topics, we'll answer them. Okay, so we'll meet at the same time Thursday.